Okay, so let's get started talking about division of polynomials. And as I mentioned in the intro video, this first topic will be about division that has no remainder. So meaning numbers that when we divide, they go in evenly. And just in case the whole concept of long division seems like a bit of a distant past memory from like 3rd or 4th grade, I am going to start with a 3rd or 4th grade division problem as our example, our starting example. So take a look at this. Before I write out my example, I want us to remember what division or long division was useful for when we were in 3rd or 4th grade. And it was maybe for something like, let's say we had a multiplication problem, 15 times 3. And if we took 15 and multiplied it by 3, we would find out that the answer is 45. Now, in elementary school, if we had 45 and we were asked to divide that number by 3, given our original fact that 15 times 3 equals 45, we would assume that the answer is 15. But long division is the method we use to prove that to ourselves. How do we prove to ourselves that 45 divided by 3 is really equal to 15? And here's how we used to do that. We would take our number out front, which in this case is 3, and we would look at the first digit, or really the largest digit. This would be the tens place, in this case, tens and ones. We look at the highest place value, which is 4, and we'd say, how many times does 3 go into 4? And the answer would be 1 time. Not evenly, right? 3 goes into 4, 3 goes into 3 once, but it could go into 4 once with 1 left over, which we figured out by saying 4 minus 3. We said 1 times 3 is 3. 4 minus 3 is 1. Then our next step was to bring down the next place, which was 5, and we would say, oh, oops, I got to write that down here. We'd say, how many times does 3 go now into 15? And we say, oh, well, that actually goes in evenly. 3 goes into 15 5 times. So I write that number up here, and to check, I multiply down. 5 times 3 equals 15. And we check, 15 minus 15 is 0. So we got that nice and even. 3 goes into 15 5 times evenly. There's no remainder, and there's no more, there are no more digits, no more numbers in our, the number that we're dividing. So we know that we're done, and we also prove to ourselves that just as we expected, 15 times 3 is 45, and therefore 45 divided by 3 is 15. Okay, that's an elementary division problem. Now we're going to talk about how that applies even in algebra in high school. And we're going to prove that by looking first at a problem kind of like we've been discussing in class. Let's say we had x plus 2 times x squared minus 3x plus 10. And let's say we wanted to multiply that out and find out what that equals. So that would be x times x squared, x times negative 3x, and x times 10. So that would give me x cubed minus 3x squared plus 10x. And then we take the second digit, and we'd also multiply that out to each of the terms in the second factor. 2 times x squared is 2x squared. 2 times negative 3x is negative 6x. And 2 times 10 is 20. And then we would combine the like terms, which we find we have a x squared here and an x squared there, so we get x cubed minus x squared, right, because negative 3x squared and positive 2x squared is just negative 1x squared. Then we would have 10x and negative 6x. That would give me plus 4x. And then we just have one constant term, so we don't have to combine that. So we get the answer of x cubed minus x squared plus 4x plus 20. Now we're going to ask ourselves the question, if we were to take this is kind of like, x plus 2 times all this stuff equals this final expression here. It's kind of like what we did here. 15 times 3 equals this larger number, 45. Here we have x plus 2 times x squared minus 3x plus 10 gives us an answer of this expression right here. And what we want to decide, or what we want to discuss, is if we were to take x cubed minus x squared plus 4x plus 20, the expression we just found, and we were to divide that expression by x plus 2, we would expect to get this other factor, right? For the same reason that we expected 45 divided by 3 to be 15. We would expect to get this solution. But the question we have to ask ourselves is, how on earth do we prove that? In this case, we had a long division process that allowed us to prove that that was true. Here, what is our process to prove that this expression divided by x plus 2 is going to give us one of our original factors? And the process we're going to discuss today is called polynomial long division. Just like we have regular long division, which we just discussed, there is something called polynomial long division. And the exciting thing about it, if you're not necessarily feeling excited, I don't blame you, because long division doesn't usually make people feel excited. But one important thing, or one thing that will make you happy, is to know that the rules are fairly similar. So let's give it a try. Let's take x cubed minus x squared plus 4x plus 20, and let's figure out how to divide it by x plus 2. I'm going to use a different color, just, so we can keep all of our numbers straight here. Oh, and actually, hold on. Let me zoom out there so you can see what we're doing. Okay, so just like in regular division, we take this expression on the outside and we compare it to the first part of our inside expression, which in this case is x cubed. And specifically, I'm going to compare x to x cubed. And I'm going to ask myself, how many times does x go into x cubed? Just like before I asked, we had our expression all right over here. We had 45 divided by 3, and we asked how many times does 3 go into 4, and the answer was 1, because 1 times 3 is 3, and 3 is smaller than 4. Here we're going to ask the same thing. What number up here, or what expression, if I multiplied it times x, we don't care about the 2 so much right now, we're looking for the leading term. What number times x, or what expression times x, is going to give us something close to x cubed? And if we think about that, we might say, well, actually, x squared times x gives us x cubed, doesn't it? Let's see what happens if I write x squared up here. Basically, we're going to take x squared and we're going to multiply it by this expression and write our answer down here. Just like over here, I had 1 over on the right. 1 times 3 is 3, and we brought that number down. We're going to do the same thing here. X squared times x is x cubed. And x squared times 2, because remember we're multiplying it by this whole expression, just like when we factor, or when we distribute numbers, we're going to distribute x squared to both x and 2. So x squared times 2 is 2x squared, and we're going to write that right here, plus 2x squared. So notice this expression here is the result of taking x squared and multiplying it times x plus 2. Now, just like over on this regular division example, in order to decide if we made a good decision, we had to subtract 3 from 4. Subtract 3 from 4, get 1. And we said, yeah, that's good, because 3 can't go into 1. So we got as close as we could get. That's what we want to prove to ourselves over here. We need to subtract the bottom expression from the top. And in order to do that, we switch the signs of everything. We're going to subtract x cubed, and we're going to subtract 2x squared, because we're subtracting everything. So one of the things I remind students is, remember the phrase switch the sign. So I'm switching the sign of x cubed to negative, and I'm switching the sign of 2x squared to negative 2x squared, so that we can subtract. x cubed minus x cubed is 0. So that looks good. And negative x squared minus, because remember we're subtracting, 2x squared gives me negative 3x squared. And that's good because we got this first term to cancel the 0, and so we know that it's good. Just in the same way that over here we wanted to make sure that 3 couldn't go into 1, and that's true. So we wanted to make sure that the x cubes went away. I know that x can still go into x squared, but it's going to be part of our next bring down. So over here we brought down the 5, and we continued our operation. 3 into 15 is 5 times. Now we're going to do the same thing here. Bring down 4x. And we can ignore this 0, right? The 0 doesn't really matter. So we have negative 3x squared now plus 4x. And I'm going to ask myself the same question I did up here in the first part, which is how many times does x go into x cubed? Now I'm going to say how many times does x go into negative 3x squared? Well, the answer is, we take a moment to think about it, negative 3x. Because if I take negative 3x and multiply it by x, I will get negative 3x squared. And I also, of course, have to share, right, to both this term and that term. So negative 3x times 2 is negative 6x. Now let's switch the signs so that we can essentially subtract. So change this to a plus and this to a plus, because if I subtract a negative, I'm adding. If I subtract another negative, I'm adding. So I'm just switching the signs. I'm going to write that here. Switch the signs. So each time we get to that part, we switch the signs to add. Negative 3x squared, or not to add, to subtract. Negative 3x squared plus 3x squared gives us 0 again, which I don't need to write, but that's good to know. We managed to cancel those. Actually, I should write that up here too. We canceled them. And then we have 4x plus 6x. And again, remember we're adding because we had to switch the signs. So 4x and 6x gives me 10x. All right. Unlike our original regular division example, we ran out of digits on our second time because here we ended up with 0. We had nothing left, but we still have one more term left in our division, our polynomial division problem. So let's bring down that last number or term, which is 20. Again, I'm going to ask myself, how many times does x go into 10x now? And we figure it out by thinking, what number times x will give me 10x? And the answer is 10, because 10 times x is 10x. But of course we have to share it with both terms, so 10 times 2 is 20. And we subtract, and well, actually we subtract by switching the signs on both, right? Switch the sign on the 10x, switch the sign on the 20, so these cancel. And then the 20 and the negative 20 goes to 0, meaning there's no remainder because there are no other terms, no extra digits, just like over here. So we know we're done, and we know we have no remainder. So let's go check out our answer. When we took this whole expression, x cubed minus x squared plus 4x plus 20, and divided it by x plus 2, we got the exact same expression that we expected to get. X squared minus 3x plus 10, because remember we were expecting that if we took this and divided it by that, we would get the other factor from our original multiplication. And we did. But now we proved it. We could actually have figured this out, the division portion, we could have figured it out even if we didn't know what the answer was going to be. Like in this case, we knew what the answer would be. We just needed to prove that it was true. We could have also been given this expression of this polynomial divided by this polynomial, and we could have figured out the answer without knowing it ahead of time. So that is our first example of a polynomial long division problem with a remainder of 0, meaning there were no extras, no extra values. That's it for this first video. You're probably still trying to process what I just did, so I'm going to show you a second example in the second topic video, but this time the example is going to yield a remainder, and we're not going to know the answer this time. So it will be a little bit different, but we'll be going through a very similar exercise. So that is it for topic 1.